At this very moment, as you sit reading this, an event is unfolding that hardly anyone on the planet is aware of. A device roughly the size of a compact vehicle is traveling through a region of space where no human has ever seen, no probe has ever ventured, and no scientific theory has ever managed to accurately forecast what lies there. This is not a modern spacecraft. It is not the product of contemporary engineering. It was constructed before the internet existed, before personal computers were common, before most of the researchers currently analyzing its readings had even been born. It operates on approximately 4 watts of energy. For comparison, the tiny bulb inside your fridge draws more power than that. And this aging, minimally powered device, originally designed to function for only 5 years, is currently beaming back information about the cosmos that is rattling the very foundations of physics as we understand it. The scientists studying its output aren't using words like curious or surprising. They're reaching for terms like astounding, perplexing, and we got it wrong. This is the tale of Voyager 1. And here's the piece the headlines leave out. It isn't merely what Voyager 1 has discovered out there that should worry you. It's what that discovery means for life here on our own planet. It's also what is happening to the probe right now in 2026 that almost nobody is discussing. And it's what's set to happen in a matter of months, a date already fixed on the calendar, marking a milestone no human civilization has ever achieved before. Keep reading, because once you finish this, you'll never look at the night sky the same way. I'm Your Name, and welcome to the channel. Hit subscribe now if you want more content like this, because we're only getting started. Let's rewind to where it all began. September 5th, 1977. A rocket blasts off from Kennedy Space Center in Florida, carrying a probe named Voyager 1. Its assignment is straightforward. Fly by Jupiter, fly by Saturn, snap some photos, gather some readings, then drift into the void and fall silent. Its projected operational life is 4, maybe 5 years. NASA anticipates wrapping up the mission around 1981 or 1982. It would be a brief, successful excursion, a postcard from the outer solar system, and then quiet. What unfolded instead is one of the most remarkable stories in scientific history, and most people barely grasp how remarkable it truly is. Voyager 1 refused to go quiet. It flew past Jupiter in March 1979, transmitting the first close-range photographs of the planet's surface humanity had ever witnessed. It swept past Saturn in November 1980 and continued onward, gaining speed with each planetary encounter, using gravity like a slingshot to build momentum and cover more ground. By the close of the 1980s, Voyager 1 had already ventured farther from Earth than any human-made object ever had, and it was still broadcasting, still sending its faint signal across the expanding distance, still gathering data, still operating on hardware that today's engineers can scarcely believe still functions. Then, in 2012, 35 years after launch, something occurred that transformed the entire narrative. Voyager 1 crossed the heliopause. For anyone unfamiliar with the term, it marks the single most significant boundary in our cosmic neighborhood. And crossing it is comparable to stepping outside everything our civilization has ever known as home. Picture it this way. The sun doesn't just radiate heat and light. It also continuously emits charged particles known as the solar wind, which blows outward in all directions, pushing back against the surrounding void, and creating a massive protective bubble enclosing our entire solar system. That bubble holds every planet, moon, asteroid, comet, every craft we've ever launched, and every living creature that has ever existed. The far edge of that bubble, the spot where the solar wind's energy finally gives out and is halted by pressure from interstellar space pushing in from beyond. That's the heliopause. It's the true physical border of our solar system. Everything within belongs to us. Everything beyond it is something entirely different. And in 2012, Voyager 1 pushed through that border and emerged on the other side. It became the first human-made object to ever exit the solar system. Not symbolically, not technically. The first physical thing our civilization has ever sent into the actual expanse between stars. And it kept transmitting. Consider the significance of that. We currently have a functioning instrument sitting out in interstellar space, not circling a planet, not lingering in the outer solar system, not hovering near the heliopause. It's actually inside the dark, frigid, ancient expanse that separates star systems, a domain no scientist, no telescope, no ground-based model has ever been able to observe firsthand from within. And it's relaying data about what that space is genuinely like. And what it's telling us defies expectations. Here's where the story takes its first unexpected turn. For decades before Voyager 1 arrived there, scientists constructed detailed mathematical models predicting what interstellar space ought to resemble. These weren't casual guesses. They were rigorous, peer-reviewed models developed by some of the most brilliant physicists working today. And those models largely agreed on one thing. Interstellar space, the plasma existing between stars, should be fairly calm and uniform. A thin, chilly, sparse environment where particles drift gradually and little occurs. A sort of cosmic holding room between star systems. Voyager 1 entered that supposed holding room and discovered it was actually a tempest. Beginning in 2017, The plasma wave detector aboard Voyager 1 started picking up something nobody anticipated and nobody could initially explain. A steady, narrow-band signal, a faint but continuous hum embedded in interstellar plasma that, according to every model designed to describe this environment, shouldn't exist in that manner. Not a fleeting burst, not a data spike easily dismissed as malfunction. An ongoing signal persisting year after year, spanning a distance exceeding 900 million miles of interstellar space. For context, the distance between Earth and the Sun is 93 million miles. The signal has been picked up across a span 10 times greater than the gap between our world and our star. Researchers, analyzing the findings, published in the peer-reviewed journal Nature Astronomy, reached a clear conclusion. Interstellar space isn't the calm, uniform emptiness that models depicted. It's turbulent. It contains structure at every scale, from distances measured in meters up to distances measured in millions of miles. In a very real sense, it's alive with movement and complexity that remained completely hidden from us because we had never before had an instrument operating inside it. Now pause and consider that for a moment. Every model ever built to explain the universe beyond our solar system was constructed from the outside, looking in, from a planet armed with telescopes, mathematics, and theory. And now, the first instrument we've ever actually placed within interstellar space is revealing that those models were missing something essential. That the region beyond our solar system is more intricate, more dynamic, and more structured than we realized. But here's where this stops being abstract and starts hitting close to home. Because those revelations about interstellar space don't stay confined out there. They circle back to us. The very bubble separating our solar system from this chaotic interstellar environment is the same bubble shielding life on Earth. The heliopause isn't merely a line on a scientific chart. It's a shield. It deflects the most hazardous cosmic radiation, high-energy particles streaming in from distant exploded stars, preventing them from reaching the inner solar system at full intensity. If that shield were noticeably weaker or less predictable than our models assume, the consequences for life on Earth could be substantial. And what Voyager 1 is revealing is that the interstellar environment pressing against that shield from outside is more turbulent, variable, and energetic than any model has accounted for. We don't yet fully know what this means for the shield's long-term stability, but the fact that we now must even ask this question represents a shift in how we view our vulnerability as a species. Now the story grows even stranger. Because before we examine what Voyager 1 found right at the boundary itself, we need to address what happened in 2023. Because in 2023, Voyager 1 very nearly died. For 5 months, the spacecraft kept sending a signal back to Earth. But what it transmitted was garbled, corrupted code, scrambled data that engineers at NASA's Jet Propulsion Laboratory, despite decades of experience interpreting everything the probe had ever sent, simply couldn't decode. The instrument was still functioning. The signal kept arriving. But whatever message it carried had become unintelligible. For a team that had successfully run this mission since 1977, nothing like this had ever happened before. The root cause, once identified, was both straightforward and alarming. A single memory chip within the spacecraft's flight data system had physically degraded after nearly 5 decades of nonstop exposure to cosmic radiation. One tiny component from 1970s technology, a chip smaller than an inch, had developed a defect that was corrupting the portion of software responsible for formatting and sending scientific data. No alert had triggered, no warning had come through. The chip had simply given out after 46 years of continuous operation in the harshest setting any human-built object has ever endured. Under normal circumstances, you'd repair a broken part by traveling to it and swapping it out. Here, the component sat 15 billion miles away, unreachable by any existing form of travel, with no rescue mission feasible on any relevant timeline. The only tools available were radio waves moving at light speed, and even those took 22 hours one way to reach the craft. 22 hours just for a message to get there, another 22 hours for a reply to return. Every diagnostic step, every attempt to investigate the issue, every test of a possible fix demanded a minimum 44-hour wait to complete just one round of communication. Picture what that troubleshooting process actually looked like from inside mission control. You examine a piece of data, you form a hypothesis about what's wrong, you draft instructions to test that hypothesis, you send them. You wait 22 hours, you receive whatever comes back from the spacecraft, you study the response, you notice something slightly off from what you expected. You form a new hypothesis, you draft new instructions, you transmit them, you wait another 22 hours. The cycle repeats patiently for months. And every step of that process carries the awareness that a single mistaken instruction, sent once across 15 billion miles of emptiness, could permanently terminate the mission with no way to undo it. The JPL team persisted through this for months, meticulously, methodically, under pressure unlike almost anything else in engineering. And they pulled it off. They determined the corrupted code couldn't be fixed in place, but it could be moved. The affected software section was broken into smaller pieces and stored across different areas of the spacecraft's available memory. Each piece was individually verified and adjusted to work properly from its new position, then reconnected to operate as a unified whole. It amounted to remote brain surgery conducted through a 44-hour communication delay on a machine nearly 50 years old sitting 15 billion miles from home. By mid-2024, Voyager 1 was back online, transmitting clear, complete, readable scientific data once more, and what it immediately resumed sending was further evidence of those persistent, unexplained plasma fluctuations in interstellar space. More readings of the turbulent structure the models had never anticipated. The spacecraft that should have expired in 1981 had returned from what might have been its final silence, and it came back with more to share. But none of that, not the discovery, not the near-fatal malfunction, not the recovery, prepared anyone for what Voyager 1 had actually uncovered the moment it crossed the heliopause back in 2012. Because this part of the story is described in scientific papers using language that stops sounding like physics and starts sounding like something else entirely. For decades, models describing the heliopause, the outer edge of our solar system, predicted what an instrument crossing it should experience. The solar wind gradually fading on the inside, the interstellar medium gradually becoming detectable on the outside. A smooth, slow transition between environments, a gentle blending at the edges, like where a river gently meets the ocean. That's not what Voyager 1 encountered. At the heliopause, particles weren't gently tapering off. They were moving at speeds approaching a meaningful fraction of light speed. They were colliding with such force that temperatures approached 30,000 degrees Celsius. Not inside the sun, not within any star, but at the outer fringe of our own solar system. Supposedly a relatively cold, thin transitional zone. Some researchers have called this region a wall of fire, and not as a figure of speech. A genuine concentration of extremely energetic charged particles forming an actual physical barrier at the edge of everything we call home. And then came the magnetic revelation. For decades, one of the core predictions about crossing the heliopause was that the magnetic environment would shift dramatically. Inside the bubble, the sun's magnetic field. Outside, the entirely separate magnetic field of the galaxy. Two distinct environments, each with its own magnetic character, cleanly divided at the boundary. Voyager 1 discovered something entirely different. The magnetic fields on either side of the heliopause were, in ways existing theory hadn't predicted, connected. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, were interacting with the galaxy's magnetic field beyond, through a process called magnetic reconnection, where field lines from separate sources rearrange and release energy in the process. The solar system and the surrounding galaxy are not magnetically isolated from one another, they're magnetically linked. At the boundary between everything familiar and everything unexplored, there exists a zone where energy is being exchanged between our home and the broader cosmos, in ways no model built before Voyager 1 crossed that line had ever anticipated. This isn't a minor footnote. This isn't a small correction to existing theory. If the relationship between our solar system and the interstellar environment is more dynamic, more interconnected, and more energetic than the model suggested, then our understanding of how the heliosphere shields Earth across geological time needs to be rethought from scratch. Now, let's turn to what's happening right now in 2026, because this story isn't finished. In fact, it may be entering its final chapter, and the timeline is tighter than most people realize. Earlier this year, NASA made a call nobody involved in the mission wanted to make. The low-energy charged particle instrument, one of Voyager 1's scientific tools that had been gathering data almost continuously since the 1977 launch, was powered down. Not because it had broken. It was still working perfectly. It was switched off because Voyager 1's power supply is dwindling, and there simply wasn't enough left to keep it running. Voyager 1 draws power from 3 units called radioisotope thermoelectric generators, essentially containers of plutonium-238 that generate heat as the material gradually decays. That heat converts into electricity. At launch, these generators produced around 470 watts. Today, nearly 49 years on, output has dropped to roughly 250 watts. They lose about 4 watts annually. At some point in the early 2030s, output will drop below the minimum threshold needed to run any remaining instrument, and Voyager 1 will fall permanently silent. The mission team has known this was coming for years. Years back, the scientists and engineers gathered to map out a careful strategy, deciding which instruments to shut down and in what sequence, to extract as much scientific value as possible from the shrinking power supply for as long as possible. Of the 10 scientific instrument packages Voyager 1 launched with, 7 have already been powered down. Deciding what to switch off and when ranks among the hardest choices any scientific team ever faces, because every instrument lost represents questions that will never be answered, and because there's no way to reactivate an instrument once you've concluded you shut it down too soon. But here's the twist barely anyone outside the JPL team is discussing. They haven't given up on buying more time. NASA engineers are currently working on something reportedly nicknamed internally the Big Bang procedure. It's an experimental effort to reroute how power flows across Voyager 1's remaining systems, aiming to squeeze out extra electrical capacity from components currently running below peak efficiency. The concept is technically intricate and genuinely risky, since even minor adjustments to power distribution on a nearly 50-year-old spacecraft with no manual override could produce unpredictable outcomes. So the team is taking the cautious route. They're testing the procedure first on Voyager 2, which has somewhat more available power and sits slightly closer to Earth, making a potential failure marginally less disastrous. Trials on Voyager 2 were planned for May and June of 2026. If those trials confirm the procedure is safe and effective, the same technique will be attempted on Voyager 1, with the earliest possible attempt scheduled no sooner than July of this year. And here's the detail that makes this genuinely significant. If the procedure succeeds, there's a real chance the low-energy charged particle instrument, the one just powered down, could be switched back on. The team remains cautious. They're not promising anything, but they're still trying. Because with Voyager 1, assuming something is finished before it truly is, has never once held up. And now we arrive at the date already locked into the calendar, certain, unavoidable, a milestone no human civilization has ever reached before, one that will occur whether or not anyone is paying attention. On November 18th, 2026, at 16 minutes and 12 seconds past 2 hours a.m., Pacific Standard Time, Voyager 1 will reach a distance of exactly 1 light day from Earth. That means it will be so distant that a signal traveling at light speed, the fastest anything in the universe can move, will require exactly 24 hours just to reach it. Send a command to Voyager for Monday morning, and you won't know it arrived until Tuesday morning, and you won't get the spacecraft's reply until Wednesday morning. 2 full days just to complete one exchange of information. No human-made object has ever been that far from Earth, not once in all of civilization's history. And on that date in November 2026, Voyager 1 will cross that threshold for the first time while still operational, still transmitting, still sending data home, and then it will keep going. Every hour, it travels roughly another 38,000 miles deeper into interstellar space. The communication lag will keep growing, the power supply will keep shrinking, and at some point in the 2030s, the final signal will arrive. But even then, Voyager 1 won't stop. Nothing in interstellar space is there to stop it. No friction, no atmosphere, no gravitational pull strong enough to meaningfully alter its course. It will simply keep traveling silently in a straight line at 38,000 miles per hour into darkness, with no end on any human timescale. And fastened to its structure, mounted onto the frame of this fading machine, is something that will outlast it entirely. The Voyager Golden Record. A gold-plated copper disc containing greetings in 55 human languages, the sound of rainfall in a forest, ocean waves, human laughter. 90 minutes of music drawn from cultures spanning human history, diagrams explaining basic principles of physics and mathematics, and a map built from pulsar positions, designed to show anyone who finds it exactly where our planet sits in the galaxy. Carl Sagan, one of the record's creators, described it as a message in a bottle cast into the cosmic ocean. And that's precisely what it is, because whoever or whatever eventually discovers it, whether another civilization a million years from now, or some form of intelligence beyond our current imagination, the record will convey something true. That a species existed here, that they were curious, that they reached outward, that they built a machine of metal, electricity, and mathematics, and sent it beyond everything they had ever known, carrying the sound of their own laughter. The record will still be traveling long after our sun becomes a red giant and consumes Earth's orbit. It will still be moving after every human city, every archive. Every name we ever carved into stone has been worn away by geology and time. It's the most enduring thing our civilization has ever produced, and it's mounted on a spacecraft currently running on less power than the bulb above your bathroom sink. Now, let's return to the science, because there's one more thing Voyager 1 is doing right now that deserves center stage. The persistent plasma signal it's been detecting since 2017 isn't just an oddity. According to the researchers studying it, it represents the first continuous, real-time measurement of interstellar plasma density humanity has ever obtained. Before Voyager 1 began picking up this signal, scientists could only capture isolated snapshots of plasma density in interstellar space, measurements triggered by specific events, like shockwaves from massive solar eruptions, traveling all the way to the heliopause and sending ripples into the interstellar medium. Those readings were useful but scattered, like trying to understand the weather across an entire continent by checking one thermometer once a year in a single city. What this ongoing signal from Voyager 1 provides instead is something closer to a continuous feed. An evolving portrait of interstellar plasma as the spacecraft moves through it, day after day, year after year. And that portrait reveals that interstellar space isn't a static, uniform backdrop. It has texture. It has weather. It contains structures built from charged particles and magnetic fields stretching for millions of miles, interacting with the outer boundary of our solar system in ways Earth-based models could never have detected or predicted. The space between stars isn't empty. It's active, full, possessing a physical character we're only now, for the first time in human history, beginning to actually decode. There's a question at the heart of all this that scientists haven't yet resolved. The persistent signal has two possible explanations, and researchers analyzing Voyager 1's data haven't determined which one is correct. The first possibility is that the emission stems from thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their surroundings. This would still be a genuinely important find, but it would fit within existing physical frameworks without requiring a major overhaul. The second possibility is that Voyager 1 is picking up something called quasi-thermal noise, a distinct physical mechanism that conveys information about plasma density and temperature in a subtly but meaningfully different way, one that would demand a substantial revision of existing interstellar medium models. Determining which explanation is correct requires either additional data from Voyager 1 itself, which is producing less each year as more instruments go dark, or a new mission specifically built to study interstellar space, equipped with instruments designed for exactly this purpose and capable of taking the measurements needed to settle the matter. No such mission currently exists. None is currently funded. The next spacecraft capable of reaching interstellar space and crossing the heliopause, even if funded and launched today, wouldn't arrive at that boundary for at least 25 years, meaning that when Voyager 1 finally falls silent, the question it raised will remain unanswered. The map it began sketching will stop being updated, and the only real-time window our civilization has ever had into interstellar space will close, and stay closed for decades. That silence is coming. The exact date isn't fixed, but the direction is certain. Every year the power drops. Every year more instruments go dark. Every year the JPL team faces tougher calls about what to keep running and what to let go. And sometime in the early 2030s, the last instrument will hit its minimum power threshold, the final signal will begin its 24-hour trip home, arrive and be recorded, and nothing will follow it. After that, Voyager 1 will simply continue moving silently at 38,000 a minute mph, carrying its golden record through the darkness, passing through regions that human eyes won't witness for tens of thousands of years, continuing a journey that began one September morning in 1977, when a group of engineers aimed a machine at the stars and pressed the launch button, expecting it to last just 5 years. Here's what I want you to take from all of this. Because there's a fact buried in the middle of this story that's easy to overlook amid the discoveries, the physics, and the engineering. Right now, in 2026, the only functioning scientific instrument humanity has ever placed in interstellar space is 48 years old. It was built with technology that predates personal computers. It runs on less electricity than the bulb above your kitchen stove, and it's sending back information that's reshaping how we understand the universe and our place within it. We've built things far larger. We've built things far more powerful. We've built things costing vastly more money, involving far more advanced technology. And none of those things has told us what Voyager 1 is telling us right now, because none of them possessed the one quality Voyager 1 had. None of them had the persistence to keep going long enough to actually get there. Some questions about the universe can only be answered from inside the universe. Not from a ground-based telescope, not from a satellite orbiting Earth, not from a mission to Mars or the asteroid belt, only from a craft that crossed the heliopause and entered the space between stars. We have exactly one such machine. It's old, fading, and running on 4 watts of power. And as long as it's still transmitting, we need to keep listening. Because when it finally goes silent, the answers to some of the most important questions we've ever asked will go silent along with it, for at least a generation. The signal is still arriving, stretched across 15 billion miles, delayed by 22 hours of travel time, carrying information about a universe stranger, more turbulent, more interconnected, and more extraordinary than any Earth-built model has ever accurately captured. One machine, 4 watts, one chance to listen. The real question is whether anyone is actually paying attention. If this kind of story interests you, subscribe right now and turn on notifications, because we're diving deeper into the edges of what science actually knows next time. Leave a comment sharing what surprised you most in this video, and share it with someone who needs to hear it, because this story deserves more attention than it's currently getting. Thanks for watching.